Okay, so as promised for part 2 of the Minimax with applications, we're happy to have André Neves tell us about that part.
Okay, so I have to thank Misha and also Harold Rosenberg for the invitation. Yeah, so I think you can hear me better now. So I have to thank Misha and Harold Rosenberg for the invitation. You know, it's definitely a great pleasure to be here. So what I'm going to do is I'll just pick off where Fernando stopped, and I will explain, you know, how to find an infinite number of minimal embedded hypersurface in a manifold. Okay, so that's the idea. So the theorem is the following, right? So every compact Riemannian manifold with, so we need two conditions. One is that the dimension is neither too small nor too large, even if this one is less serious than that one. I'll explain that shortly. And the second one is that the Ricci, the metric has a positive Ricci curvature. So if I have a manifold which satisfies these conditions, then there is an infinite number of minimal embedded hypersurface. Okay, so let me make some remarks about this. So the first remark is that when n equals 1, so when n plus 1 equals 2, the theorem is false. And the reason is because of one word I forgot to write, which is, then there's an infinite number of minimal, oh yeah, I wrote it, okay. So the reason is because of this word, that we get an infinite number of minimal hypersurface, and they are not immersed, they are embedded. And there are ellipsoids in space which have only 3 simple closed geodesics, and every other geodesic will have self-intersections. So the theorem is false because there are ellipsoids with only 3 simple closed geodesics. On the other hand, Fernando mentioned this result, and I have to mention here as well, is that Franks and Bangert in '92, they showed that every two-sphere admits an infinite number of closed geodesics. Of course, they're going to be badly immersed, and they're going to have lots of self-intersections. Okay, closed geodesics. Okay, and the third remark is also, Fernando also mentioned that, is that we were motivated by a conjecture of Yau from '82, and Yau's conjecture was that every three-manifold, compact three-manifold admits an infinite number of minimal immersed surface. So Yao, I think he has 2 or 3 versions of this conjecture. You know, he restates this conjecture in 2 or 3 surveys. In the first one, I think it's the first problem in the minimal surface section in the first problem list he gave. He states immersed, and then later on, he asks for just an infinite number of minimal embedded surface. I think the reason why he puts immersed here is because he knows that just on S2, with any metric, the result is false. Okay. And I should say that for hyperbolic, if M3 is hyperbolic, or if it meets a hyperbolic metric, then this is known. Then this is known. This is true by Kahn-Markovich. This was from 2012, or Rubinstein. So their approaches are different. Rubinstein was in 2005. So Kahn-Markovich, what they do is they find an infinite number of essential surface of arbitrarily high genus. And then as soon as you have that, you can just minimize area there or minimize energy, and you get an infinite number of stable immersed minimal surface. Rubinstein, he has a different method. He looks at Hagar splittings of many covers of M3. But Rubinstein, he outlines this very carefully, but he does need to use the index estimate, which, as Fernando said, has not been proven yet. Okay. So what I will explain now is how to find this minimal hypersurface. So in our theorem, we are as far from hyperbolic as possible. And usually, in these type of problems, there's a big difference between the hyperbolic world, in which it's very rich in topology, and so you find the geodesics or the minimal surface by finding lots of topology in the ambient manifold, or the case where you have positive reach or your manifold is a sphere, in which case you have no topology at all. And so if you want to find minimal hypersurface, you have to look at the space of all hypersurface in a given manifold. Okay? And so in the case you are considering, the ambient manifold could be a sphere, so there's just no topology at all. And so the basic approach is the following. So I'll describe the basic idea to prove that. So the key space to consider is the space of integral cycles with mod 2 coefficients. And let me be less rigorous than Fernando and just define this as the space of all closed embedded hypersurface. And then you can put a suitable topology, and you complete the space with that topology called the flat topology, and this is what you get. So this is the completion with respect to the flat topology of the space of all closed embedded hypersurface. And we put Z2 coefficient because we don't care about the orientation. A surface, a hypersurface, are the same hypersurface with different orientation. They are the same object. And here, there's a natural functional, which is the volume functional. And so to any element there, the volume of an element in this space is just Fernando defined it as called the mass. In this setting, the volume is called the mass of T. Okay. And critical points of this functional, if they are smooth, they are called the minimal hypersurface. So minimal hypersurface are smooth critical points, meaning critical points with smooth support of the volume function. So what the theorem is saying is that in some cases, we can make sure that this function will have an infinite number of distinct critical points. Okay? So let me explain that part, because the whole issue hinges on a fact which is him subtle a priori, but actually is tied down to very deep facts about the structure of that space. So let me explain that now. I'll keep the theorem here, and we can erase this. So from the basic principle of Morse theory, or min-max theory, as Fernando explained, if I want to have an infinite number of critical points, I must have a lot of topology there, right? And that has been settled by Almgren. This was his thesis. So Almgren, there's an important theorem of Almgren in '62, where he showed that the ith homotopy group of that space, it does relative homotopies to 0. This is equal to 0 if I is bigger than 1, and Z2 if I equals 1. So every homotopy group vanishes but the first one. Okay? And so this theorem in particular, this implies, hence, this space is weakly homotopic to RP infinity. So RP infinity is the easiest space you can think of, which has the first homotopy group Z2 and every other homotopy group 0. Okay. And so if the spaces have the same homotopy groups, they are called weakly homotopic. And so if I want to look at it, if I want to understand the topology of this space, I might as well just look at RP infinity, in which the topology is easy to understand, right? In particular, we can then compute the kth singular homology, right? Because so then we get that the kth singular homology of this infinite dimensional space with coefficients mod Z2 just has one generator to the power of k. So there's a lambda bar, we call lambda bar. It's a generator of H1, and that generates the whole homology ring of this space. Okay, if you just do cut powers there. Okay, so so now I'm going to explain what the crucial issue is. So the RP infinity has infinite topology, and so we should expect that any function in RP infinity should have an infinite number of critical points. In particular, the volume functional, which is defined in this space, weakly homotopic to RP infinity, should have an infinite number of critical points. But what is the key issue? Let me write that even in. The key issue is that if sigma is a critical point, is a critical point for the volume functional, then 2 sigma, 3 sigma, or any multiple of it are also critical points. Okay? And so in particular, this would be my infinite number of critical points. So they count as critical points, but of course they are not geometrically distinct. So this is a thing we need to rule out, and this is one of the most subtle things of this Almgren and Pitts min-max theory. Okay? A priori, this just seems some minor or technical issue, but understanding why this is not going to happen when we try to find this minimal hypersurface that turns out to be tied down to lots of subtle facts about the topology of these guys. So this is what I'm going to try to explain now. So this is the first ingredient of the approach. So let me do now the second ingredient. So we want to have, on RP infinity, there are for every k, there's a k-projective plane, which is homotopically non-trivial. So we want to make sure that we capture these k-projective planes on this other space. So we're going to have a definition to capture that. So that's the notion of k-sweep-out. So given, say, X, a cubical complex, we say a map phi from this cubical complex into this infinite dimensional space is a k-sweep-out. So, of course, a continuous map. If, when I pull back this element in k-singular homology, I get something non-zero. So one can think of this, it's not, but we can think of this guy as being the volume form of the k-projective plane you have there. And what I'm saying is that if I pull back the volume form of this k-projective plane, I get something non-zero there. So that's called a k-sweep-out. Okay? And now we have this notion of k-sweep-outs. One can start doing min-max theory. Let me do that. So the third ingredient is to define the k-width, omega km, as we look at all possible k-sweep-outs and then we maximize the volume for every k-sweep-out. Okay? So this definition might look a bit exotic, but there's a context from which this was motivated in which we can see this guy appearing in a natural way. And that is in the definition of the kth eigenvalue for the Laplacian on a closed manifold. So there's a Rayleigh quotient definition of the kth eigenvalue, which says that if I want to compute the kth eigenvalue of a closed manifold, then what I do is I do the nth for every k plus 1 plane P in W12. And then for every k plus 1 plane, I maximize the energy, or the Rayleigh quotient. For every function in W12, which lies in the plane is non-zero, then I maximize the Dirichlet energy over its L2 norm. So here we do the same thing. Instead of minimizing among k plus 1 planes, we minimize among k sweep-outs. And then instead of maximizing on the k plane, we maximize on the particular k sweep-out. So Gromov, he calls this the nonlinear spectrum of the manifold, because his motivation was this. So this is like a nonlinear spectrum. Okay? And Gromov, he looked at this quantity, and later Guth, they also looked at it. And the theorem we need to use, this is due to Gromov and Guth. So it's Gromov and Guth separated by 20 years. So Gromov in 87 and then Guth in 2007, what they showed is that there exists some constant depending only on the ambient manifold, such that this k width grows like the n plus 1 root of k. So I will sketch the proof of this upper bound, but let me just say that the representative of the k sweep-out that Fernando constructed violates this upper bound badly. The area for Fernando representative was growing linearly, while Gromov-Guth will be able to find one where it grows like the n plus 1 root. Okay, so I'll explain this. So the fourth ingredient, that's the Almgren and Pitts min-max theory, min-max theorem. So Almgren and Pitts min-max theorem says that each of these numbers I can realize as the volume of some minimal embedded hypersurface, but of course I have to take into account that I could have many disjoint components, each with its own multiplicity. Right? So one way to write is to say that this k width equals the sum when j goes from 1 to some large integer nk of nkj times the volume of some sigma kj, where these numbers are all positive integers, and this set sigma kj, or sigma k1, all the way to sigma nk are minimal embedded hypersurface, all disjoint. So no two of these guys intersect. Okay. And of course, I'll repeat this. The problem is that we want to rule out just having a finite set there and just out of integer combinations being able to express every possible number there, in which case there's no contradiction. Okay. Okay. So what I'm going to do now is I will sketch briefly how to put these 4 ingredients together to prove the theorem, and then I will explain how this upper bound follows, because that's a very elegant argument of Larry Guth, which he has used in other cases of his own research, and I think it's is a useful thing to know. And then, if I have time, I'll just mention some more open problems related with the behavior of this k width.
So where does which parts of these use
Ricci?
Which parts use the Ricci curve?
I'll say that now. Okay. So yeah, just at the end, just at the end. Yeah. So the ingredients have nothing to do with positive Ricci. Let me erase this. Okay. The dimension, it's used, the dimension between 3 or higher is used in that theorem. So if we want to have this, where this guy is being smooth and embedded, this is only true if the ambient dimension is between 3 and 7. If it's 8 or higher, then these guys will have a singular set with very small size. If the ambient dimension is 2, then this is not true. What is true is that you can realize as stationary integral variables, but they have a worse structure than smooth guys. Okay. Okay, so yeah. Okay, so let me explain the strategy for the proof. Let's do a sketch of the proof. Okay. So the first step is to use what's called the Lusternik-Schnirelmann theorem to show the following. If omega, if the k width equals the k plus 1 width for some k, then there are an infinite number of minimal embedded hypersurface. Okay, so let me make some comments about this. I will not explain how to prove this. I'll just motivate why should we expect this to to be true. So the proof uses what's known as Lushnik-Schnillman theory. And the basic idea is the following. I think the analogy with the kth eigenvalue there is a good one for this case. Whenever the kth eigenvalue equals the kth plus 1 eigenvalue, then you have a whole one parameter of eigenfunctions. So in particular, we have a whole infinite number of critical points for this quotient. So that's the same phenomena there. The one case in which it's easy to understand this statement is the case for ellipsoids, right? If we take an ellipsoid, then we can do this in a way that there are only 3 simple closed geodesics, right? It's going to be, which is the intersection with the coordinate axis, right? Let's put. So there's one here. Let me put the geodesics in blue. Or maybe green, because the blue cannot. There's one geodesic here. This is another geodesic. And this is another one there. Okay. So we can do this in a way that the length of these 3 geodesics are all distinct. So in this case, the shortest geodesic, this will be omega 1. Then the second shortest geodesic, let's say that this one, would be omega 2. And the third shortest geodesic, this would be omega 3, right? If the second and the third geodesic, they have the same length, then we have a whole one-parameter family of geodesics, right? Because then the ellipsoid will have some rotational symmetry, and we get a whole one-parameter family there. So this fact comes from some topological fact first found by Lushnik and Schnillman. Okay. So let me not say anything else about that. So this is the first step. So the second step, the second step is to assume the opposite of this, which is that the sequence is strictly increasing. Because if the sequence is not strictly increasing, then by the first step, I already know I have an infinite number of those. So I can assume that this sequence is strictly increasing. Okay. And now, that's where we use the positive Ricci, is that the positive Ricci condition implies by Frankel Theorem. So Frankel Theorem says that if you have a manifold whose ambient curvature has positive Ricci curvature, then any 2 minimal hypersurface must intersect. Okay. So in particular, when we go to Almgren and Pitts, Almgren and Pitts says that I can realize these numbers as a finite linear combination of volumes of minimal embedded hypersurface, which are all disjoint. And so the only way this can be true if you have positive Ricci is if you only have one of those. Right? So Frankel Theorem implies that the k-width has to be written just as, using that notation, and low index k would be 1. And so this would just be n1k times the volume of sigma k1. Okay. And so now we can finish the argument, because we assume that this set, suppose that all these minimal embedded hypersurface is a finite set, meaning I'll have repetitions as k goes to infinity. So assume that this set, 1, 1, sigma 2, 1, sigma k1, assume that the cardinality of this set is finite, meaning I only have finitely many distinct possibilities there. Okay. Then, using the fact that the sequence is strictly increasing, that's a simple combinatorial argument. Assume. Then, the first step, or the second step, So it's a simple combinatorial argument to see that if I only have finitely many possibilities, and if these numbers are strictly increasing, then these guys have to grow linearly on K. Okay. Then second step implies that this K width grow linearly on K. But on the other hand, I know from this Gromov-Guth theorem that they grow less than linearly. They grow like the n plus 1 root. And so that's where we get the contradiction. And so, but this contradicts the Gromov-Guth theorem. And so in particular, the sets we get there, they have to be, you know, an infinite number of those. So what I'm going to describe now is how to understand where does this upper bound come from. And then I'll just mention some more open problems, and we'll just finish. So the thing I want to explain now is this Gromov-Guth theorem. So let me write here. So I want to explain the following. Gromov-Guth is that the omega km, I'll just put like this, is grows in the same proportion, or is grows less than this number. Okay, so let me explain this. So I want to explain this. So in order to even try to understand that, we must at first have at least one case sweep out so that we can do something with it. And this Fernando already mentioned, so let me review that. So let's first construct a case sweep out. Let's first construct a case sweep out. Okay. So let's pick some Morse function on F, some Morse function. Okay. And now, out of this Morse function, for every k, we're going to have a map from some k projective plane into the space of flat cycles with coefficients mod 2. Okay? And the map is given the following way. Phi k, if I take the first, if I take some point there, so I use projective coordinates, a0 to ak, then this is going to be the boundary of the set of points where a0 plus a1 f of x plus ak. So I'll explain what this is. So we take k plus 1 points, we make a polynomial on f, and then we look at the zero set of that polynomial. Okay, so let's just see what is a 1 sweep out. And then we'll see also what is a 2 sweep out, and from that we are able to imagine what every k sweep out will look like. So let's just put k equals 1, right? So if we do k equals 1, then if I'm computing this guy, let me, I can just use the fact that I'm doing a projective coordinates. So this is the same thing as just this guy. If I divide everything by a1, right, assuming a1 is non-zero. And so this is, by definition, the set of points where lambda plus f equals 0, which is just the inverse image of minus lambda. Okay? So if there's my manifold, and f goes from the real line, then as lambda goes from infinity to minus infinity, then I'm literally just sweeping out the old manifold, right? So this would be the inverse image of minus lambda, right? So this is exactly that first representative that Fernando drew. Now let's do the second one. So let's do here as well. So now if I do this guy, then the definition, I can do the, I mean, it's irrelevant for this case. So the definition is that this is the zero set of A naught plus A1F plus A2F squared. And so for certain values of these guys, I can decompose this into a two-level surface, right? So this will be the inverse image of one level surface, or one level surface union with the other level surface, where T1 and T2, they're going to be the roots for the polynomial A naught plus A1X plus A2F squared, X squared, where T1, T2 are roots of A naught plus A1X plus A2X squared. And so the need for this coefficients mod 2 is that when the polynomials have two roots and they degenerate, become 1 and then 0, in that case, I could imagine two-level surface just coming together, having multiplicity 2 and then 0, and that's continuous if you use coefficients there too. Okay? So the typical element here is going to be two-level surface. So this will be the typical guy. And when the polynomial will have one root, we could imagine as this two-level surface coming together, start having multiplicity 2, and then just disappearing. Because if you use flat topology for coefficients mod 2, this is a continuous deformation. Okay, so that's the advantage. So that's why we need to use that two coefficients. So the remark is that that K sweep out fails miserably for the K width, because if I look at the K sweep out, that the typical element will be K level sets of F, and so the area should grow linearly on K. And Gromov-Guth is saying that it's going to grow like the sublinearly. Okay? And so I'm going to explain now the argument. Okay. So notice that a typical element here is going to be the inverse image, the union of several inverse image of the function f, where j less or equal than k, and so the supremum of the volume is at least linearly in K. So now I will describe a good idea to pin it down this to less than linearly. Okay, so let's just describe a good argument. Okay. So the first thing to do is to decompose M into K disjoint cubes. I mean, not disjoint, but just intersecting along faces, right? Into K cubes of length, of side length, proportional to 1 over K n plus 1, the ambient dimension, okay? So this is M. So let's imagine that this is just the ambient manifold M. And so we consider a cubication of M like this. Okay. So let's introduce some notation where it's important to keep track of the center of the cubes. So let me put here. CK, this is the center, the set of the centers of the cubes. So it will be here, 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 these guys. And so on. So now the second step is to tilt the Morse function f, tilt the Morse function f so that the each level's surface of f intersects at most one center of all the cubes, so that the intersection of a level surface of f with the centers of the cubes, the cardinality of this is always less or equal than 1 for all t. So so a level hypersurface of the function f will look something like this. So I can intersect this guy, and then I'll miss it there and there. So this would be a typical level hypersurface. And if I perturb t, then I get some other level surface, which will intersect, say, some other center, but will intersect no other center, for instance. Could be like this. The what? That's right. It doesn't matter. So when the roots aren't real, then this set will either be the 0 set or everything, in which case, when you take the boundary, you get the 0 element. Okay? So a good example is to just imagine, so you can imagine that your polynomial is like this, right? And then keeps moving up. You know, as you move the polynomial, becomes like this, and then becomes like that. So I can imagine moving the coefficient so that the polynomial behaves this way. Okay? If you look at the level hypersurface, here will be two guys, one guy multiplicity 2, and then the 0 set. But because guys with multiplicity 2 are 0, because I'm using coefficients mod z2, this operation is continuous. I can just imagine the points, right? I have 2 points, 1 point multiplicity 2, and then 0. And this is continuous in the flat topology. Okay. So I drew here two different level hypersurface. Okay. So now, out of this, the idea is to construct now the competitor, which will be a K sweep out, and whose maximum volume will be of that order. So then we set psi k be a map from RPK into the space of 2 cycles, where psi kx, so the definition, I'll write it and then I'll say what it is. The definition will be just the radial projection of each element phi kx, because remember that each element phi kx, each element here is just a union of a level hypersurface. And so this is the radial projection of phi kx away from the centers of the cube, away from the centers of the cube, onto its boundary. Oh, did just erase the Gromov-Good theorem? It's OK. Onto its boundary. So let's do a picture there. OK. So if I do this here, then what I'm going to get is, so this guy, on each cube, I do a deformation retract of the cube minus a tiny neighborhood of the boundary on minus a tiny neighborhood of the center onto its boundary. So the thing will look like this. Here, this guy will go like that, and then like that, like this. Now, there's this exceptional bad point where the level hypersurface just intersects the bad point, and in this case, the guy just stretches out and then keeps doing this. It's going to be like this, like that, and like that. So I do this for, OK, we can barely see. It's OK. I do this for the, let me do in white. OK, white's not good. Let me do in orange instead, sorry. I do this for this guy, and now I'm going to do this for the second guy. And this is a crucial part of the argument, is that when I do this for the second guy, I'm going to have lots of cancellations. Because, for instance, I do it for the second guy, and this will go here. Now, here is going to cancel. It's going to appear with multiplicity 2, so it's going to cancel. This guy is going to go like this, and then it's going to go like that, and then like that, where was like that and like that. But the pointed point is like here and there, at all these steps, when I add them up, they're going to be with multiplicity 2, so they will cancel. Okay. So I have this element I radially project onto the faces, and I'm going to get lots of cancellations. And that's how I'm decreasing the area dramatically. And now when I'm going to count the area, I'm going to use the fact that there were lots of cancellations at the boundary, because each time something appears multiplicity 2, that's 0, to get the correct estimate. OK, so let's do the count. So now I can count the volume of this guy. When I define, this is by definition the volume of the radial projection. And I'm going to count this where I do the radial projection. So the typical element here is a union of level hypersurface of F. So I do the radial projection of those which intersect a small neighborhood of the center, plus the radial projection of those which miss the center by a fixed amount. Okay. And so now I can estimate this. These guys, so I have here k fibers at most, and there's at most one element which hits one of the centers. And so I can estimate this by at most k fibers, and there's at most one bad guy, which is this one that gets stretched, where the area will be at most the sides of the cube to the power of n, right? It's going to be k minus n to n plus 1. Now, when it goes to this guy, this is where we use the cancellation. So these guys will all be projected onto the n faces of these k cubes. So in particular, I'm going to get at most the cardinality of the number of n faces of all cubes, all k cubes, times the area of each face. And the area of each face, of course, is going to be proportional to k to the side, to the n power there. Okay? And of course, when I do this, so this number, this is just k1 over n plus 1, and I have k cubes. The number of faces is some multiple depending on n, but not on k, on k. So I can just forget about the multiple depending on n. So this is also of the order k times k minus n over n plus 1, and this has the order of k1 over n plus 1. Okay? And so this was the argument for the upper bound. So in the 5 minutes I have left, I'll just mention some more open problems related with the structure of these numbers. Erase this here. So let's mention some open questions. So the first one, that's due to Gromov. And it's whether a Vi law holds for the K nonlinear width. So the conjecture would be that the limit when K goes to infinity of this K width, if you divide by its growth rate, then you should have a universal constant that just depends on n times the volume of the manifold to the appropriate scaling power. Okay. And so there's been some progress here, progress by Lukumovich and Glenn Addy. And I should also say, so this is some progress. Let me mention some non-progress, is that this is not known even for S2, not known for S2. And a lot of the problems that I'm going to mention, and a lot of the questions that Fernando and I keep asking, they are philosophically speaking, they're asking, to which extent does the analogy with the K linear eigenvalue extends to this K width? So for instance, when Fernando wrote the conjecture that under positive Ricci, this K width should be attained by a multiplicity 1 minimal hypersurface with index K, that's equivalent to the standard result in spectral geometry of Karen Uhlenbeck, where she says that for a generic metric, the Kth eigenvalue is attained by eigenfunction, by a simple eigenfunction, multiplicity 1. So we are all inspired by these questions on the linear eigenvalues. So the second one, and the second one is to understand what is the optimal map that gets asymptotically close to omega k. So what is the map psi k that is getting asymptotically optimal? And here we have a suggestion, which I'll mention because I think there's a nice connection with the spectral geometry part. And so one possible suggestion for the maps which are getting asymptotically to this K width is to look at the first Kth eigenfunctions. So phi naught, this is the constant, phi 1, phi k, and so on. This is the first k eigenfunctions for the Laplacian. Then out of this, we can consider a map from RPK into this space, which is just the zero sets of all possible linear combinations. So phi k of A naught to AK, this will just be the zero set of A naught, phi naught plus A1 phi 1 plus AK phi k equals 0. Okay? And the remark is that if this map is getting asymptotically optimal, then this would imply a conjecture of Yau on the size of the nodal sets. So if, say, the limit as k goes to infinity of the k width over the supremum of the volumes of this map phi k equals 1, then this implies some then this implies that the volume of the kth eigenfunction, the zero set, it's called the nodal set, that this grows less than k to the power of 1 plus 1. And in particular, this would imply Yau conjecture, or one side of the Yau conjecture on nodal sets. Nodal set. And the final one is that it's an incredibly subtle problem to try to compute this k width just for the round S3, right? So the first four are easy to do, right? The first width, the second width, the third width of the round S3, and the fourth width, they're identical to 4 pi, right? And one way of seeing this is that, as Fernando explained, we have 4 linear eigenfunctions. So the space of the lowest eigenvalue, the lowest eigenvalue on S3 has multiplicity 4. So that's one way of seeing that we have here 4 pi. And then, interestingly, to compute the fifth width, so I have a student who's working on that. He was able to figure out that's 2 pi squared. And that's, of course, related with the proof of the Wilmer conjecture. I don't think you can prove that the fifth width is 2 pi squared without having the Wilmer conjecture as a byproduct. And so he computed this, and he also computed the 6 and the 7 width. That also 2 pi squared. But then, he also computed that the 9 width is strictly bigger than 2 pi squared. And he has an argument to show that it's also strictly less than 8 pi. And of course, the fascinating question would be to pin down its number. Okay. So I'll just stop here. Thank you for your attention.
Any questions for Andres?
Yeah. So in the case of S3, it also has this result. Every topological type being realized.
Every topological type?
Of closed surface being realized as a
that's right,
surface in S3. So it basically covers all the topological types.
That's right.
So I'm asking, maybe you have implemented minimal surfaces for VT bigger than 0. Let's say 3-dimensional manifold. Any analog, like not only infinite many, but also covers all the topological types.
Yeah, so that's in general a fascinating question. So as I say, our existence theorem, our theorem just exists as theorem, but a priori, one does not know whether the area goes to infinity or the genus is going to infinity. Our proof doesn't provide that. I consider it's a fascinating question to try to pin down what's happening geometrically to this surface. I would conjecture that the area goes to infinity and the genus goes to infinity. Okay.
Do you know that they're orientable?
On S3, they will be orientable for sure. In general, yeah. So if you do an RP3, you can start getting non-orientable guys. Yeah.
So in step 1 that you listed, do you have, in this case, do you have one parameter family?
Well, no, it doesn't. No. We would expect that, but no, we don't have that. You just know that you get infinitely many. So the argument is by contradiction. You suppose they are finitely many, and you show that 2 of them cannot be equal. Yeah.
I'm curious, what do you expect?
I would expect that for bumpy metrics, these numbers should be strictly increasing, right? Because, with your analogy, for bumpy metrics, minimal surface should come isolated. And so if the one width equals to the other, in my mind, I would see like one parameter family, and that cannot occur. So I'd expect that for generic metrics, the k width are strictly increasing. Just like for generic metrics, no 2 eigenvalues are ever the same. They are strictly increasing.
Anyone else? Okay, thank Andre again.